So let us start with the next lecture, that is Oswald dilution law. Now Arrhenius' concept of acids and bases, it was expressed quantitatively by Oswald and in the form of the dilution law in the year 1888. Means whatever was told by Arrhenius qualitatively, it was put forth by Oswald in quantitative manner. You can explain this Oswald dilution law, that is HA, if it is dissociating in this way, double arrow, it means it is dissociating weakly in aqueous medium. This is also in aqueous medium. H plus and A minus ions are formed. So HA is nothing but the undissociated and the partly dissociated H plus and A minus ions are formed. So for this, you can write Ka equals to, for this particular one, you can write Ka. What is this Ka? Ka is nothing but a dissociation constant of acid. Now the solution of weak acid or weak base, it contains undissociated molecule along with a small number of ions at equilibrium. Isn't it? Means for this you can write Ka as H plus ions at A minus ions, concentration of H plus and A minus ions divided by concentration of an acid. So this is your Ka. Ka is nothing but the acid dissociation constant. Ka means acid dissociation constant. Okay. You can write same for the bases also. When like if I write the general reaction as BOH, it dissociates as B plus and OH minus ions in aqueous medium. This is also in aqueous medium. So you can write Kb will be equal to concentration of B plus concentration of OH minus ions divided by the concentration of a base. So where this Kb is nothing but a base dissociation constant. This is base dissociation constant. Okay. Now suppose if we want to quantize this suppose we take 1 mole of acid is present in V volume of the solution. Means we are considering here volume also and the concentration of the acid also. Means suppose we take 1 mole of acid HA, acid HA is present in V volume, in VDM cube of the solution. So at equilibrium, what will happen? The fraction which is dissociated would be alpha. So alpha is nothing but as we already discussed, alpha is nothing but a degree of dissociation. So this is, you can write degree of dissociation of an acid. So the amount which is left undissociated, that you can write as 1 minus alpha, because we are taking here 1 mole of acid. Out of this 1 mole of acid, if alpha is the amount which is dissociated, so 1 minus alpha would be the fraction of an acid that remains undissociated, isn't it? That is undissociated portion here. Okay. So at equilibrium, this concentration, when I write this in square bracket, it means the concentration. So concentration of acid, it would be equal to 1 minus alpha upon B. Means this 1 minus alpha, that is the amount of acid which remains undissociated divided by the volume, because we'll be taking here some volume of the acid of the 1 molar concentration. So here 1 minus alpha upon B. So this is the concentration of this in moles per dm cube. This is the thing at equilibrium. Because at equilibrium, what will happen? Some of the ions will remain undissociated and some will be dissociated into their respective ions. So concentration of H plus ions equal to concentration of A minus ions will be equal to alpha divided by V. This is the situation when it attains equilibrium. So this is again at equilibrium. So this is the concentration of acid at equilibrium. This is the concentration of H plus and A minus ions in equilibrium. And this is nothing but a 1 minus alpha is nothing but a fraction which remains undissociated, and this is the fraction which is undergoing dissociation here. Now, if you substitute this in this equation, I'll write this equation again, that is of Ka. We know that Ka is equal to concentration of H plus, concentration of A minus divided by concentration of Ha. So if you substitute the values in this equation, if this number, this has equation 1, and if you substitute this in this equation, so Ka can be written as Ka will be equal to, what is this concentration of H plus ion concentration, alpha upon V. You can see here alpha upon V at equilibrium. For this A minus also, it is alpha divided by V again, divided by Ha, that is 1 minus alpha upon V. You can see here, it is 1 minus alpha upon V here. Okay, now to continue further, we are having this equation. This is your equation 1. We are having the equation number 2 also. I'll write here only Kb for this base dissociation constant. That is Kb will be equal to B plus OH minus concentration of OH minus ion divided by BOH. This is your equation number 2 here, and this you can number this as equation number 3. Okay. Now if we put some concentration here, if C is the initial concentration, if I write if C is the initial concentration of an acid, initial concentration of an acid in moles per dm cube, and B is the volume, it is the volume in dm cube per mole, isn't it? Okay, so then you can write concentration will be equal to 1 by V. You can see here concentration, that is inverse of this volume. According to this units also you can write C equals to 1 by V. Now replacing this 1 by V in equation number 3. So what is your equation number 3? We'll go back to this earlier slide. Equation number 3 is this one. So you can replace this 1 by V by C. This 1 by B, you can replace this by C here. So you can get your equation Ka will be equal to Ka equals to alpha square into C divided by 1 minus alpha. For your convenience only, I'll write this equation number 3 again. Okay, on this slide itself. What is this equation number 3? Ka is equal to alpha upon B into alpha upon B divided by 1 minus alpha divided by. We have substituted the concentrations. Now this you can further simplify it as alpha square. B will get cancelled, and it would be remain with 1 minus alpha into B. V square will get cancelled, and it is 1 minus alpha divided by V. So it is left with this alpha square divided by 1 minus alpha into V. Okay. Now we are having this equation in front of us. This is your equation number 3 actually. Okay. Now instead of this C here, we have got C equals to 1 by V. Now replacing this 1 by V in equation number 3 here, in equation 3 you replace this 1 by V by C. So instead of this you can write, instead of this 1 by V, Here you can write alpha square into C divided by 1 minus alpha here. So we are just replace this 1 by V from here. So we are left with alpha square into C divided by 1 minus alpha. So here we got alpha square into C divided by 1 minus alpha here. This is your equation number 4. You can number this as equation number 4. Now for weak acids, alpha is very small. That is why we call it as a weak acid, means very small amount is dissociated into its ions. So you can write 1 minus alpha, that is the undissociated portion is nearly equal to 1. Okay. This is happening only when alpha is very small. Now this equation number 3 and 4, both the equations can be written as Ka will be equal to, instead of this 1 minus alpha, you can write only 1. So Ka will be equal to alpha square divided by V. This is your equation number 3. You can write in this way. And the equation number 4, you can write Ka equal to, instead of this 1 minus alpha, you can write this, instead of this, you can write 1. So Ka will be equal to alpha square into C. So we arrived these two equations, this one and this one also. Now both this equation can be rearranged also in terms of alpha. So alpha can be written as alpha equal to, instead of alpha square, you can write under root of Ka divided by C, or you can write alpha will be equal to under root Ka into V. So we got these two equations again in terms of alpha also. So I just rearrange the equation in terms of alpha. This is in terms of, this is rearranged this way, and this I rearrange this way also. So this will be your equation number, next equation number 5 and 6. If you number this as a 6, this will be your equation number 5. Now this equation number 6, if you look at this equation number 6, it shows that degree of dissociation of weak acid, it is this equation number 6, it shows that it is inversely proportional to the square root of the concentration. You can see here, this equation number 5, it is inversely proportional to the square root of the concentration, or directly proportional to the square root of the volume, isn't it? Containing 1 mole of the weak acid. Now similarly, you can write for the weak bases also. Same equations you can write for weak bases also. Alpha will be equal to square root of Kb divided by C, and alpha will be equal to square root of Kb into V. So these equations can be used to solve the problems based on this. So if I write all the 4 equations, there are many problems you are supposed to solve based on this. Number 1 equation, I'll write again. Alpha equal to percent dissociation divided by 100. We have studied this in the first lecture. Second equation, Ka, that is acid dissociation constant, equal to alpha square into C. Third, you can write alpha equals to, this thing we are just saying, Kb divided by C, or alpha equal to square root of Ka divided by C. And the fourth thing, you can write alpha equal to, in terms of volume, Kb into V, or alpha equal to Ka, square root of Ka into V. So all these 1, 2, 3, and 4 equations can be used to solve the problems based on this. So I'll be giving you the PDF file for this problems based on all the 4 equations. Thank you.